Okay, we will see the frequency domain representation of AM signal, amplitude modulated signal, or spectrum of AM signal. Okay, frequency spectrum of AM signal. Okay, so we have a time domain signal XT. This is total amplitude modulated signal. So I will get this signal omega CT plus AC mu MT is the message signal, cos omega CT. So this is the time domain signal. Okay, so this is the time domain signal. And to find the frequency spectrum, we have the time domain signal. Then this time domain signal, okay, this time domain signal should be converted to the frequency domain signal. Okay, so that is capital X omega. Okay, so this is the frequency domain signal. Okay, to get the frequency domain signal from this time domain signal, what is the tool we can use? We can use Fourier transform tool. No? We can use Fourier transform. So to find the spectrum of AM signal, what we have to simply do? We have to get the Fourier transform of X is total modulated signal. Okay, then we can get the Fourier transform of this two signal SC plus CT plus AC mu MT cos omega CT. Okay, so here we have a plus sign. Okay, if we have a plus or minus sign, okay, between these two terms using linearity property, we can write this F AC cos omega CT plus AC mu MT cos omega CT is also Fourier transform. Here also we have to get the Fourier transform. So we can evaluate this term Fourier transform and this term Fourier transform separately, then we can add. So we can get the full frequency domain signal. Okay. So if we consider this part, okay, okay, so if we consider the Fourier transform of this cos omega CT, okay, if you find the Fourier transform of this signal using first principle, you will get this signal 5 delta omega minus omega C plus 5 delta omega plus omega C. This term you will get. Okay. Here half come. No, half not come. Okay. So you will get this. Okay. So you will get this. Okay. So to get this value, you have to get the Fourier transform of cos omega CT. Okay, cos omega CT. Okay. So you have to evaluate this integral. Okay. To get the Fourier transform of this cos omega CT minus infinity plus infinity cos omega CT e to the power minus j omega t dt. Okay, so this is the Fourier analysis equation. Okay, Fourier transform analysis equation. To get the Fourier transform, we can use this. Okay, so this is the cos term. Okay, so in integration we have cos term and exponential term. We can simply convert this cos terms into exponential terms. Okay, so here we can convert this cos omega CT into exponential terms using Euler formula. Okay, so you will get EJ omega CT half plus half E minus J omega CT like this. Okay, so you have to multiply these two terms using e to the power minus j omega t, e to the power minus j omega t. Okay, so you will have two terms. Okay, so 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 if we evaluate, we can get the Fourier transform of delta t function. Okay, using the definition of this delta t, you can get the Fourier transform of this delta t, and it will come as 1. Okay, so there is the property called duality property. So using that duality property, we can get the Fourier transform of 1 as 2 5 delta omega. Okay, this is the impulse response, impulse function in frequency domain. Okay, this is the impulse function in time domain. Okay, so we have get this Fourier transform for 1. Okay, so here it is 1 and e to the power minus j omega t. Okay, so we can consider it as a time shifting signal. Okay, so using that time shifting property also, you can get this value. Okay, in my signal and system tutorial, I have explained how we can evaluate this. So I'm not going to do it here. So if you want to know how this is how we get this answer, you can refer that signal and system tutorials. Okay, so here we get this function with the Fourier transform as a known fact. Okay, so it is phi delta omega minus omega c, phi delta omega plus omega c. So this is we get as a known factor. Okay, so using this fact, we can write the Fourier transform of this signal. Okay, what about this signal? So in same manner, you can go that principal analysis and you can do that integration and you can find the Fourier transform of this signal. But I think in our first session, we discuss about modulation theorem. Okay, so in modulation theorem, what it said, if we get the Fourier transform of xt, any xt value multiplied by cos signal, you will get the Fourier transform this one. Okay, so we can use this result to evaluate the Fourier transform of this part. Okay, so if I write this part, Fourier transform of this part, AC mu mt cos omega ct. Okay, so this mu AC are constant, so I can get it out. Mu AC can get out. Okay, so I have mt cos omega ct. Okay, so here the function is mt and here the function is xt. So if we think the Fourier transform of mt is m omega, capital M omega. Okay, so we can write this as capital N omega minus omega c, here half come. Okay, and half mu AC there, capital N omega plus omega c. So likewise, we can write this. Okay, so what is the total, what is the final answer? So if we get the Fourier transform, if we get the Fourier transform of x a m t, okay, we will get for this signal, we will get these two terms. Okay, that is phi delta omega minus omega c plus phi delta omega plus omega c. Okay, and also we get, so this is for carrier signal. This is for carrier spectrum. Actually, this is the carrier spectrum. Okay. Okay, and here we have, so this is the sideband. Okay, so this we can say that this is a sideband. So that sideband spectrum, we get this. Okay, so we have half mu AC capital M omega minus omega C plus half mu AC M capital M omega plus omega C. So, so this is the sideband spectrum. Okay, so this is the sideband spectrum. This is the carrier spectrum. Okay, so we have two spectrum. Okay, so if we think that this MT we don't know. Okay, MT we don't know what is this signal. Okay, and if we get the Fourier transform of this MT, we know it is M omega, but we don't know the signal. Okay, let's say this signal is like this. Okay, we just take the arbitrary signal. It is just like this. Okay, so let's say this omega 1 and this omega 2. Okay, so this signal is look like this. Okay, so if we draw the frequency spectrum of this general signal, okay, this is omega. Okay, and this is 0. Okay, so first we will draw the carrier part. So here 5 delta omega minus omega. Okay, so delta omega is like this. This is delta omega. It is in 0. Omega minus omega C means is shift to this way by omega C. Omega plus omega C means it shift to this way by omega C. Okay, so I write it. Okay, if this is the 0 value, here we have omega C minus omega C, here we have plus omega C, and here we have 2 impulse. This is 2, 5, this is 2, 5. This 2, 5 is the area of this impulse. Okay, we will get this. Okay, and if we consider this spectrum, what happened? You can see that this spectrum, if it is omega 1, omega 2, say this is 0 line, this is 0 line. Okay, so this is minus and this is plus omega 2, say like this. Okay, so you can see that omega minus omega naught means this total signal shift to this way by omega C. So this central point come to the omega C point, omega C, and you have this omega 1 and omega 2 between, okay, omega 2 like this, and omega C will be in between this 2, 1. Okay, so this signal is centered it at omega C. Okay, and also if it is omega plus omega C, so it is shifted to this way, and also this spectrum is centered at plus omega C minus omega C. So you will get here the signal will like this now. Not like this, in this manner. Okay, and here also in manner. Okay. So here it is in minus omega 1 plus omega C. Here minus omega 1 minus omega C, this point. And this point is omega C minus omega 1. This point is omega C plus omega 1. So you will get this kind of spectrum. Okay, so bandwidth of the AM signal we consider as this difference between these two signals. So here it is omega M, omega 2 minus omega 1. Okay, like this. So you get. Okay. So this is the frequency domain representation of AM signal. So you have to understand this. Here we get two signal. to carry a peak, and also we get two sideband, not two sideband actually. Here the sideband is spectrum. Okay, you have this sideband spectrum, two separate spectrum there, two peak. Okay, so normally sometimes we consider only this plus part. Okay, plus part. So at that time we are not considering this one and this one. We only focus this one and this one. Okay. So in some books, I think our reference book also, this part and this part is only mentioned, but this one and this one should be available. It is not mentioned there. Okay. Only this part and this part. The plus side spectrum is only plus side spectrum is shown. Okay. But minus side spectrum is also there. Okay. So in our sometime in some books this is in not in omega, it is in f. Okay, so this is the angular frequency and this is the frequency. So you know that how this related to phi f is equal to omega. Okay, so if this is in f terms, sometime this 5 is not available here, and sometimes 5 may become here like this. Okay, so you can do the Fourier transform in this using this term also. Then you will get sometime you will get this 5. Okay, 5 inside the inside this spectrum terms. Okay, so that is the only difference. Okay, so both way is correct. Okay, so you can find the spectrum in omega domain, that is also frequency domain, and also in f domain, that is both correct. Okay, now we will move to the question. Okay,